My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Today is our 249th International Physics webinar, and I'm happy to share with you all that today we have with us Dr. Tami Pereg-Barnea, Madam, Associate Professor, Department of Physics, McGill University, Canada, and she has already connected with us. And she will talk on quantum materials and collective phenomena. I think you will enjoy this session, and you can also join with us by this link. I will send this link in our comments section. You can join with us through using this link, and you can also ask question by commenting. So I think you will enjoy this, and thanks all for supporting throughout this 1.5 years. So, Madam, I would like to welcome you in our International Physics webinar. It's our honor and privilege to host you in our International Physics webinar, Madam. And I think our students and viewers will delighted by listening your
Thank you so
speech.
much.
And you
Thank you
can
so
start,
much.
Madam.
It's really my pleasure to be with you today. And I'm sorry I can't be there in person. I'm really curious. So maybe
Yeah,
one
of
day.
course, I will invite you. If
Maybe
the
one day
situation
we'll
will
have.
improve. Yeah, of course, Madam.
Thank
That
you
will be
so
better.
much.
That's my
Thank you
pleasure.
so much. So we're making the best of the situation we have.
Yes.
So today I prepared a very basic introduction to quantum mechanics and quantum materials. And you will see that actually quantum mechanics is the theory that governs all materials and is the theory that predicts what kind of material properties we will have. And let me start with the very basics. I don't know in which stages of studies people are, so we'll start very slow and we'll get to other things later. So I want to talk about my research. So what do I do? I'm a physicist, I'm a theorist, I work on quantum materials. Physics, all of you should know, is a science that describes the world through mathematical theories. But all we do is actually describe. We don't prove anything. We actually try to minimize the amount of assumptions and write a consistent theory that describes all of the evidence we have logically derived from these assumptions. A theory is a coherent mathematical description that agrees with current experiments. And also, if a theory is good, it will have some predictive power. So you will be able to not just explain things that already have been seen, but predict the result of an experiment that hasn't been seen yet. And quantum materials is the study of materials. Usually these are not materials we find in nature. These are materials we make in the lab. And their properties, if you want to understand them, they are understood through quantum tools. And this is because we're basically interested in low temperature. And in low temperatures, the important players of a material are usually the electrons, which are quantum particles. And we talk about how they move, how they collide, and how they conspire to give us the properties that the material has. So let's start. So when I first started graduate school in Canada, I'm from Israel, by the way. 20 years ago, I came to Canada and I wanted to study physics. And I wasn't sure whether I want to do theory or experiments. And through experience, I learned that I prefer theory. But what's a theory? A theory is when we see something, we have some evidence, and we think, aha, this is a hat. And this is a very famous drawing here in Quebec from The Little Prince. And you might think it's a hat, but actually it's a snake that swallowed an elephant. But we have no way to know that unless we develop our theory, right? Unless we develop our theory further and make some predictions. If I think it's a hat, I know that if I turn it around, I should see a hole for my head. But if I think it's a snake, I might not even want to pick it up. So a theory cannot be proved. And I'll give you an example of a theory. One day I come home, and this is my carpet, and I see crumbs on the carpet. I have a theory right away. My theory is that my son ate some crumbs, but when I come to ask him, he has another theory. He says that a big monster came and ate cookies on the carpet. However, I might have some more evidence on my son's face. So we have evidence. And if this was a trial in court, we would say, aha, we proved the theory that my son ate the cookies and not the cookie monster. However, in physics, you can accumulate evidence that support your theory, but you can never prove it. You can say, I'm convinced beyond some reasonable doubt, but there's no way you can know what happens in all energy scales, in all length scale. So sometimes we think we understand something, like Newton thought that he really understood the world around us through mechanics, classical mechanics, but he didn't know that the Newton's laws do not hold for very small particles. So there's always the chance that our theory will be disproven, but there's no way to prove it. Nevertheless, a theory is useful. So we don't need it to be correct in every scale of energy, in every scale of length, and so on, but we need it to be useful. It is useful if it helps us understand what is happening. So, for example, in my university at McGill, we do physics, both experimental and theoretical. And it turns out that we need to do a different physics for any kind of length scale that we have. So we have physicists that think about the universe. So these are 10 to the 26 meters in scale. Galaxies, our solar system, climate is much smaller scale. And then there's the physical scale of things that we live in, like 100 meters for the physics building. And then we go smaller. On the right, you see, I don't know if you can see my cursor, but you see what looks like snowflakes. These are actually graphene samples grown on a nanometer scale. And you can look at DNA. This is even smaller. And here we really get to nanometers. These are mesoscopic materials that only have a few hundred of atoms in a structure. And you can go much, much deeper and look inside particles. This is our particle physics. So what I'm trying to say is that you really do need a theory that is useful in the scales at which you're interested. So today I'm going to talk about quantum mechanics. If you want to talk about a cannonball launched somewhere, or you want to talk about a tennis game, you don't need quantum mechanics. Classical mechanics is just as good. So we shouldn't be worried about quantum mechanics at these scales. However, if you want to describe particles in a solid or particles by themselves, you have to think about quantum mechanics. So this is our scale that we care about, the nanometer scale, where you know that you have a few hundreds of atoms per nanometer. And these are the scales that are important for determining material properties. And as I said before, for the everyday world, you need to think about classical mechanics. The main difference between classical mechanics and quantum mechanics is that classical mechanics is deterministic. So if you're trying to think of what will happen now with a ball and a tennis racket, All you need to know is the initial conditions. If you know where the ball is and you know its velocity, you can easily find its trajectory. You know what it does. And Newton's laws were basically written for that. You know that the acceleration is proportional to force, you know the action-reaction, and you know inertia. And with these three simple rules, you can calculate any trajectory. However, in quantum mechanics, things are very different. As I said, they're important in the microscopic scale. They're not relevant to our everyday world. They're relevant inside the materials. And quantum means discrete. So where does the word come from? It comes from the fact that if you take a particle and confine it to a very small scale, and you can think of an electron bound to an atom, or you can think of many electrons bound to your metal, then the energy becomes discrete, and we call these discrete lumps of energy quantas of energy. And as I said, it's the confinement that leads to that. And therefore, small systems are described by quantum mechanics. However, quantum mechanics is non-deterministic. So what does that mean? It means that we can't know where the particle is and what its momentum is at all times, like we know for the classical particle. We basically settle for a much less knowledge. We want to know probabilities. What's the probability to find a particle at a given place at a given time? So we have to give this up because of the uncertainty principle. But it turns out that this is already enough to give us a lot of predictive power. And in that sense, quantum mechanics is non-deterministic, but it is very successful. If we didn't know quantum mechanics, you wouldn't have a phone, for example, because all of our technology, all of our electronics is done by semiconductor industry, which if we didn't understand quantum mechanics, we wouldn't know how to build it. Okay, so let's start with a classical particle. You all know, think of a tennis ball. It has a position which you can follow over time. And for example, if it's a free fall, you know how to write the equations of motion. You know the acceleration is minus g, pointing down. You know the velocity. You therefore know the position at all times. That's great. Of course, with friction, it becomes more complicated. Interestingly, the energy is a continuous number. If you want more energy, you either increase the potential energy by going higher, or you increase the velocity by going faster, you'll get more energy. Every value of energy is allowed. On the other hand, we have waves. And let's start with classical waves. So this is the face of the sea. There are many waves there. Of course, the simplest wave is just a cosine omega t that you see below. The wave is not a particle in the sense that it's defined everywhere. You should think about it as a function. For example, in the sea, the height of the water is a function. It's defined everywhere. It can change in time, and it can change with space. It doesn't have momentum or position, unlike the particle. And it does have a frequency and a wavelength. So I can ask, if I look at the wave below, how fast do these maxima come to a certain point or pass a certain point? That would be the frequency. And the wavelength would be what's the distance between these consecutive maxima. These are classical waves, and we describe them by a wave function, a scalar function of position and time. And the simplest example here is the wave on the left, A naught cosine kx minus omega t. Okay, what's the hallmark of waves? A hallmark of waves is interference. So if you take a wave front coming from the left here, plane wave, and you pass it through two slits, it's just like having two sources for circular wavefronts. And then if you want to ask what's the amplitude on the screen that we're seeing the wave, the amplitude would depend on whether you have constructive interference or destructive interference. So if the path from one slit plus the path from the other slit gives you both high amplitude, together it's going to be higher. But if one is high and one is negative high, it will actually average to zero. So you would get no amplitude. So basically on the screen, what we see is an interference pattern. You might have seen it in a lab. You can point a laser through a slit and see an interference pattern on the wall. So this is really the hallmark. This is what you would see if you did that experiment. In quantum mechanics, actually the notion of waves and particles is mixed. In what sense is it mixed? So first of all, we have some particle nature of light. And this was found by the photoelectric effect in 1887 and explained by Einstein in 1905. So the idea is the following. If I shine light on a metal, which has free electrons, some electrons are emitted. And it turns out that if you want electrons to be emitted, you must give them enough energy. But I don't know what's the energy of the light. It turns out that there's a threshold of frequency. So if I give a very low frequency light, there's no electrons emitted. Only if I pass a threshold, electrons are starting to be emitted. And that actually points to the resolution by Einstein that said, actually, you don't need to think about a wave when you think about the photoelectric effect. You need to think about particles. These particles are called photons. They have momentum which is proportional to their wavelength. So momentum P is h bar k, where k is the wavelength. It's the wave number. And they have energy which is proportional to their frequency. And then all you have is a simple collision between particles. And if the photons give enough energy to the electrons will be knocked out of the material, and you'll see the photoelectric effect. On the other hand, we have a wave nature for electrons. Electrons are elementary particles. And in accordance with quantum mechanics, we need to describe them by a wave function. So we usually call it psi. It's a function of space, r, and it's a function of t. And when we want to calculate the probability to find our particle at position r and at time t, we take the absolute value squared of that wave function, and that gives us the probability density. We can, and this is very interesting, actually do the same double slit experiment with electrons. So even though I know that I have particles and I can shoot them at the double slits one by one, in the end of the day, I'm going to get an interference pattern. So from the left, look at panel A. This is the screen behind the double slits. So as I start shooting the electrons through the double slit on the screen one by one, it looks like they're just hitting the screen at random positions. As I add more and more, I just keep hitting the screen at some random position. But in the end of the day, when you look at many of these particles, it looks like the positions were not exactly random, because they did give us this interference pattern. So in some sense, they did expose to us their wave nature because they interfere. And of course, there's this important aspect of waves, which is superposition. You remember we described the interference pattern, and we said that in order to calculate the amplitude on the screen, you need to add up the amplitudes from both slits. This is superposition. Waves can always add in amplitude, and to make that more pictorially, Schrödinger wrote the notion of Schrödinger's cat, which can be in a superposition of two states. It's either dead or alive. Actually, this is the first instant when we talked about a qubit that nowadays we are using to try to build a quantum computer. A qubit, unlike a classical bit that's either 0 or 1, can be in any superposition of 0 and 1. And in the same way, the cat can be in a superposition of dead or alive until we make a measurement. So if we make a measurement, we actually have forced the cat to decide whether it's dead or alive. In a quantum computer, we have a system of quantum bits. We don't know their exact state. They are in a superposition, each of them are in a superposition of 0 and 1. We can do a quantum computation that basically, if you want to think about it, it's like making all of the possibilities of computations as if one was 0, the other was 1, one was 1, the other was 1, and so on. And in the end of the day, we measure and find one of the possible outcomes. So quantum mechanics is not deterministic. Our friend Einstein actually didn't like that at all and said, I am convinced that he, God, does not play dice. He didn't like the fact that the system decides what a state is only at the measurement, like playing dice. However, Stephen Hawking, who died a few years ago, said, so Einstein was wrong when he said God does not play dice. Consideration of black holes suggests not only that God does play dice, but that he sometimes confuses us by throwing them where they can't be seen. So now we know that, yes, quantum mechanics is very successful. So we do stick to that non-deterministic theory. And also, it's very hard sometimes to verify our predictions. And just one more word about Einstein. Even though he was opposed to quantum mechanics, he contributed a lot to the advancement of quantum mechanics. Because by playing the devil's advocate and coming up with thought experiments that can show how unintuitive quantum mechanics is. At the time, this was called the Einstein, Podolsky, and Rosen paradox, because Einstein showed that quantum entanglement leads to what he called spooky action at a distance. You have two entangled particles, you let them fly away, you measure one, and that determines the state of the other. So Einstein saw that as a reason to doubt quantum mechanics, saying that there's non-locality that's very weird in quantum mechanics. At the time when he proposed that, it was just a thought experiment. But nowadays, actually only 6-7 years ago, we were actually able to do some of these experiments and show that indeed quantum mechanics hold, even though its predictions are not intuitive at all. Some victories of quantum mechanics. So first of all, what we have on the left are spectral lines. I talked about the fact that if you confine an electron to a small place, like an atom, it only has certain energy levels. Now, if an electron is at the ground state, it's at the lowest energy level. If it's at some excited state, it may actually decay to its ground state and emit the excess energy in the form of a photon. So we see light coming out of materials. Very ancient technology was, for example, the Mercury lamp. The Mercury lamp had a gas of mercury in it, and you would pass a current through that gas to warm it up. Some of the atoms gained enough energy to be away from their ground state, and then they would relax into their ground state by emitting photons. But surprisingly, they didn't emit white light, which is photons at all given frequency. They only emitted spectral lines. So only certain frequencies were allowed. Why only certain frequencies? Because only certain energies are allowed. So when the photon is emitted, your atom goes from a given state to another allowed state, not to anything in between, because these energies are simply not allowed. So these are spectral lines. We use them, for example, in astronomy to figure out what stars are made of. We look through our telescope and collect the light and see what's the spectrum. And nowadays we know for every material what spectrum it emits. And of course, the other thing is electronics, for example. We know all about metals, insulators, semiconductors, and we can build devices out of them. And now I want to talk a little bit about electrons in solid. An optical microscope can take us to less than a micron, but that's not enough to actually see the particles, because the particles in an atom, in a material, for example, take a copper wire, and you want to see the copper atoms, the distance is about a few angstroms. So it's the nanoscale, and 10 angstrom is nanometer. So what we need in order to see what happens inside a solid is a scanning tunneling microscope. So this is a microscope that you basically have a tip. Let's see. Yeah. You have a tip which is atomically sharp. It's made of course, atoms, but the tip might be just a single atom. And you kind of run it across the sample that you want to study. And you ask, what is the tunneling current? And you record the tunneling current as you change the voltage between the tip and the sample. This is one thing you can change. And another thing is you can actually scan and go over your sample. Now, what does it give us? So first of all, what is tunneling? Well, a classical particle, if you have a particle, then vacuum, then the sample, the classical particle will not go through the barrier. However, a quantum mechanical particle can actually tunnel. So if you look at that last atom at the tip, if it has electrons surrounding it, and there's a bias voltage between the tip and the sample, the electron might hop to the sample. However, it would only hop to the sample if the energy it has is exactly an allowed energy in your material. So you are basically, by changing the energy, the bias voltage, this is the energy that your electron will get in the process. By changing the bias voltage, you're asking for an electron how many available states are for a given energy. This is what we call the density of states, and we can actually scan that. And that actually gives us beautiful images. Nowadays, this is already, almost 20 years old, maybe 15 years old. Nowadays, we have atomic resolution of these scanning tunneling microscopes. And what you can see here is the following. Every time you see, this is a gold surface with cobalt atoms that have been put there actually by the same tip. So the tip can dip into material, take an atom, and actually move it and put it somewhere else. So They were arranged in this ellipse or corral shape. And what you see inside that looks like standing waves are basically the density of electrons. So the electrons feel that they have been confined on the surface. So there are some electrons that are free to move on the surface. But once you confine them inside the ellipse, they make certain plane waves. And it turns out they took this particular shape of an ellipse because it turns out that the waves can feel whether you change something in one focus of the ellipse. Because of interference, you can actually see something happen in the other focus, and they called it a quantum mirage. The important thing here is that we actually see density waves in the electrons. So the electron density is modulated, and we can actually see that. And this has been used since the technology was developed, has been used in so many materials. And I think one material that really drove the advancement of the technology is high TC superconductors. We want to understand a lot about superconductors, and there are still many mysteries, even though we've known them for 30 something years. So technology was actually developed further in order to study these materials, because this brings us very, very close to seeing the wave functions of electrons. So now I want to talk about collective phenomena. So we talked about a single particle being described by a wave function. However, sometimes when you put many electrons together, they don't just behave like single electrons, but many of them. They actually decide that in order to minimize their energy, they should do something else. Now, why does that happen? It happens usually because of the competition between kinetic energy. Okay, the electrons want to just move around the lattice, that's kinetic energy, and potential energy. Okay, there's the periodic structure of the lattice, but more importantly, there's interaction between the electrons. So if you have interaction between the electrons, they might want to avoid each other, or if there is interaction through lattice vibrations, the atoms move a little bit, they might be even attracted to each other, all in order to minimize their interaction energy. So first of all, here's my electron. You might think that when I put voltage across my metal, the electrons start to move. That's true, they move and they're drifted by the voltage, but they don't move this way. They actually move something like that. Why is that? It's because of collision. And actually, that's the reason why we get Ohm's law. So instead of putting a voltage, which is a force on our electrons that pulls all of the electrons, instead of the voltage creating acceleration to the particle, it just creates velocity. And the reason it creates only velocity is exactly what I just showed. Instead of going straight, the electrons just collide many times. So they have an average velocity which is proportional to the voltage, and they don't have acceleration on average, because every time they accelerate a little bit, they bump into each other, they bump into the atoms, and they lose memory of their direction. So then you have to accelerate them again and again and again, and on average, we get Ohm's law. On the other hand, in superconductivity, this doesn't happen. In our copper wires, all of us have copper wires that carry electricity from whatever electricity power plant you have to your home. As the electron travels in the copper wire, due to all of these collisions, the wires warm up and we lose a lot of energy to this heating process. However, electrons in a superconductor travel without scattering. Somehow, these collisions don't happen, and there's no loss of energy. So that's the main thing of superconductivity. Therefore, you can transmit more current, you lose less energy, and you can use, why do you need more currents? For example, I can create a large current in a loop and create a large magnetic field, which is used for research, which is used for medical imaging and so on. And on top of it, the superconductor is a perfect diamagnet. What does it mean? When there is a magnetic field in the vicinity of the superconductor creates opposing currents that cancel this magnetic field. So the magnetic field cannot penetrate the superconductor. Now, if you look at the graph here, for a non-superconductor, and you measure the resistance, this is basically the energy loss in the process of carrying current. Then as I lower the temperature, the resistance might actually go down a little bit, but at zero temperature, I might still have some resistance. And that's actually true for most materials, even very good metals, they have resistances at low temperature. However, for a superconductor, it doesn't even have to start as a good metal. It might have very large resistance at high temperature. But as soon as I reduce the temperature, at some point I hit a critical temperature. At that critical temperature, a phase transition happens and the resistance just drops immediately to zero. And it persists to be zero all the way to 0 Kelvin. And that's what we call the superconducting state. So it's a low temperature phenomenon. Here I'm just showing medical imaging. This is an image of the brain, an MRI image of the brain that we need high magnetic fields to produce. Without superconductors, we couldn't have done that. This is the Meissner effect that I talked about. If your sample is not superconducting, for example, maybe it is above the critical temperature, then the magnetic field lines will just penetrate. If, on the other hand, it is a superconductor, the magnetic field lines will go around the superconductor. And here, so because of the pandemic, I actually have, I had given a lecture at home through Zoom, and a demonstration that I usually do live, I had to do at home, and these are my kids playing with the kit. So what I have here is this Petri dish filled with liquid nitrogen. So liquid nitrogen is able to cool things up to 70 Kelvin, minus 200. And what I have in it is YBCO. So YBCO is a superconductor, a member of the high TC superconducting family. It's very easy to grow in a lab. You just mix a few powders, warm them up, let them melt, and then you can create that sample. And we cool it down. Let's see if the movie works. We cool it down using, just a second, so let's try to make that. Yes, so we cool it down using the liquid nitrogen, and then this cube that you see on top is actually a magnet. And you see that the magnet is levitating above the superconductor. You can't actually put it on the superconductor. There's always going to be a little gap because the superconductor pushes an opposite magnetic field that takes it. So let's move on. So the question is, how does it happen? Why is it that we have superconductivity? And how come, I just told you about all of these collisions, how come these collisions simply don't happen in a superconductor? So first of all, let's think of what's a collision. Classically, I think of two particles moving, colliding, and then redistributing the momentum and energy between them. So you start with momentum P1, P2, it's a collision, and then you end up with P1 prime, P2 prime. That's a classical collision. In first year of physics in university, you learn how to calculate the outcome of collisions if you know the initial state. Okay, so it's a change of momentum, but altogether the momentum is conserved, altogether the energy is conserved. However, quantum mechanically, it might happen that the final states simply do not exist. Because we talked about having, in quantum mechanics, only certain allowed energies. So what if the energy for the first particle is allowed, but the energy for the resulting momentum after the collision is not allowed? And maybe the same for P2. If they're not allowed, the collision will simply not happen. So the particles will just continue with their own momentum as if they don't see each other. Now, classically, this just can't be. We can't understand two particles being at the same place at the same time and not colliding. But quantum mechanically, we certainly understand them. Because if each and every one of them is described by a wave function, then they could be at the same place at the same time. Their amplitudes just add up. So really, this notion of a collision and so on is not exactly accurate when we think of quantum particles, because they're not really at one place with a given momentum. They're everywhere with some probability of being somewhere and some probability of having a certain momentum. So the collisions simply don't happen because the energy is quantized. And at low temperature, the system wants to minimize its energy, so it might just stay in its ground state. And this is actually what happens in a superconductor. There is a ground state for the system that includes all of the particles. It's called the BCS ground state after Bardeen, Cooper, and Schrieffer, who wrote the theory of superconductivity. There are, of course, other states, but the other states are further in energy. So there's an energy gap, Eg, which is larger than the temperature, which means that if we lower the temperature below this energy gap, then thermal energy cannot give us enough energy to take the system out of its ground state. So this is a collective phenomena because the particles in the ground state are all arranged in a single wave function that describes all of them, where they are on average and what their average velocities are and so on. This is what we call the superconducting condensate. And this condensate you can think of as a large collective which has a large charge. And if you add a magnetic field, for example, it can move, but they all stay together. I want to summarize, but since I have more time, I might explain a little bit more. Actually, Pretam, I don't know, do you want to finish and leave time for discussion, or should I go on for a little bit longer?
I think you can go on because
Okay.
it's just 45 minutes and we can discuss later.
Okay, great. So let me just say, summarize, and then I'll go to explain a little bit more of what happens inside the superconductor. So as we say, the quantum mechanics is suitable for the microscopic world. However, the materials we see in our macroscopic world sometimes behave with a collective phenomena of electrons, and the collective phenomena can be understood through quantum mechanics, and that gives rise to certain properties. And superconductors are the results of quantum mechanics. So let me just talk for a little bit about superconductivity, maybe 5 more minutes, and then I'll leave time for questions. So first of all, some of you already covered that in thermodynamics and in statistical mechanics, that particles in nature are divided to two kinds, bosons and fermions. Boson particles are basically integer spin particles, and they're usually not matter particles, like photons. The number of photons is not conserved. You can create more photons by having more energy or reduce the number of photons because another particle has swallowed that energy. But what bosons do is that they basically mediate interactions. And that's how we view light. Light is a mediator of the electromagnetic interactions. And this was written beautifully by the quantum electrodynamics theory by Feynman that kind of thought of two electrons, for example, interacting through exchanging a photon. But photons, for example, are bosons. The statistics of bosons is such that they can all occupy the same quantum state. They don't have a limitation. And therefore, if you take many bosons and you lower the temperature, all of the bosons will be in the ground state. The ground state of the single particle. They will all be in the same state, and that will give you the ground state of the whole system. We call that the Bose-Einstein condensate. Bosons do not carry charge usually, and an example of a boson is actually helium-3. So helium-3 atoms are bosons even though they're made of matter particles, because sometimes composite particle that is made of an atom and a few electrons together make a boson. And helium-3 atoms are bosons. And as we lower the temperature, they create a Bose-Einstein condensate, which means that they are superfluid. They are not charged, so we don't see superconductivity, but they do flow without any friction. They don't collide with each other because they're well coordinated. They're all in the same state. Electrons are fermions, on the other hand. Fermions are often charged. They have a half integer spin. And the important thing is that they cannot all be in the same quantum states. So if I have one electron in the ground state of the atom, and then I have another electron, it cannot be in the ground state of the atom unless maybe one has spin up, the other has spin down. So then if the ground state has spin up and spin down, and that's it, the third electron that I have to, that I want to put in the same system will not be in the ground state, will be in some excited state. So this way we actually fill energy levels. So it's true for an atom that we fill the energy levels of the atom by electrons starting with the ground state and raising the energy every time we add a particle. It's also true in a metal or in an insulator. In any solid, you have an energy dispersion, so you have different energy levels. And as you add more and more electrons, the energy of the next electron you put in is larger. And actually, the energy of the most energetic electron, we call the Fermi energy. So by definition, all electrons have different states, and they could collide with each other, and that's how we get metallic states. And that's how we get Ohm's law. However, electrons can also arrange themselves in Cooper pairs. Cooper pairs are bound states of two electrons, and they are bosons. And therefore, they can Bose-condense. And the collective Bardeen-Cooper-Schrieffer ground state I mentioned before can be viewed as a collection of Cooper pairs. So if I have electrons, they would collide with each other and so on. However, if I have Cooper pairs, they can all just condense and give me the super fluid, which is now charged, and it's a super current. And therefore, I have superconductivity, a current that can flow without any resistance, without any collisions. Why would electrons pair, you might ask? Well, it turns out that Coulomb interaction is repulsive. So you don't expect electrons to be attracted to each other and be in a balanced state together. However, if you think of some other interaction, there might be some glue that connects the Cooper pairs together. So the glue could be, and that depends on what kind of superconductor you have, either the conventional glue, which is phonons. The lattice atoms are vibrating, and as they vibrate, they create an excess of positive charge somewhere. Let's think of two atoms coming together. There's an excess of positive charge. This excess of positive charge is attractive to two electrons. So effectively, the two electrons are attracted to each other. This happens at low temperature, and that's why the conventional superconductors, which were found in 1911, I think in Mercury first, these have a very low transition temperature because the energy that the phonons can give us is very low. So we suspect that the material is a conventional superconductor if its transition temperature is very low. If it's not as practical as the high TC superconductors, because in order to cool a sample to a few kelvins, you must use liquid helium, which is very expensive. And this is explained by the BCS theory from 1957. Unconventional superconductivity is mediated by magnetic interactions. So even though the interaction, the Coulomb interaction is repulsive, once we add magnetic consideration, what the spins are doing, we might actually find a net attraction. And that leads to a much higher critical temperature because the energy scales involved with the magnetic interactions are much larger. And therefore, liquid nitrogen, like I've shown you, is enough. The unconventional superconductors, I think everybody now agrees that they're not mediated by phonons, but there are still many mysteries about what's going on with these high TC materials. But here I want to really stop and answer questions if you have. I'm happy to hear what you have to ask.
Thank you, madam, for your wonderful presentation. We have got few questions. So if you allow, we can start our discussion session. The first question, what is the hydrodynamic electron flow in quantum materials?
Okay. So this is a relatively new branch. So there are regimes where we can think of the electrons as a liquid and as flowing hydrodynamically. But that really depends on the interactions you have there. I'm not an expert on that. It's not something I do. Usually it's at higher temperatures. And it's, so it has to do with thinking about the electrons as a liquid. And this happens either in very, very certain circumstances or higher temperatures. And that, of course, will have an effect on material properties, but usually on higher temperature material properties.
Thank you, madam. We have another question. So can you please tell me about that experiment?
Which
And
experiment?
maybe there is a related question. Why there's some spike? Maybe your slide, you can go your slide, and there is a picture, maybe some spike over there.
Yes. This
Yeah, first,
experiment?
could you go the first few slide?
Maybe
Maybe
this one.
not this one. Could you go back? Yeah, this one maybe. Yeah, this
This one?
spike. Yeah, maybe.
Okay. So here, the electrons are shot one by one, and then they go through a barrier that has two holes. Okay, that's the double slit experiment, or two actually slits, very large holes. Um, and you would think classically that they either hit the barrier and go back, or they go through the slit. And if you just think of tennis balls going through the slits, if you shoot them in random directions, going through the slits shouldn't change anything, and they would just go and hit the screen in random positions. And that's sort of what you see in the beginning. However, if you really want to calculate the result of what will happen when you did it many, many times, you resort to statistics. And in order to understand the statistics, you have to look at the wave function. And the wave function is a wave. It describes a wave of probability. And when I look at my screen, let me show you, just like here, I need to think of where am I calculating on the screen. And I need to think of the way, the path that my particle took from one slit to the screen and from the other slit to the screen. But if it's really a wave, I need to add up the amplitude of the two waves. And that gives me the interference patterns. And somehow we're not surprised at all when that happens with light. But when this happens with electrons, this is quite surprising because we thought of them as particles. But really, they are waves in that respect. So the only measurement that is done is in the end when they actually hit the screen. But before that, they behave as waves, and we didn't interfere with the measurement.
Okay, thank you, madam. We have another question. So now we need to go in inbox. So the first question of inbox is, what is quantum entanglement?
Okay, great. So quantum entanglement, best understood with spins. So let's say I have spin half and it points up. And then I have another one and it points down. If I know that this is up and this is down, they're not entangled because I can measure one of them. It doesn't affect the other. However, let's say they're in a superposition of down up and up down. In that case, when I measure one of them, at that point it has to decide whether it's pointing up or pointing down. Okay? So if they were in a superposition of up, down, up, and I measured and I found that this one is up, I know immediately that this one is down. This means that the two electrons I started with were entangled. Okay, they were not in a state that can be described by a product of a state for this spin and a state for this spin. It was a superposition of two such states. And once I made the measurement, I had to actually choose between the two terms in the superposition. You can think of this as dead and this as alive. I made the measurement. I found that it's alive, okay? If it's alive, I only measured this particular one, but I already know the state of this one. This is quantum entanglement for spins. You can think of entanglement in many different ways, but it basically happens when you have a system of more than one particle, and it's described by a many particle wave function. and measuring one of them will affect the others.
Okay, madam, thank you. Now we have another question, and this is related to this question. So please explain spin.
Okay, spin. So spin is something that doesn't have a classical analog, but we do have a mental image. So spin is an angular momentum. So when I take a rigid body and I start rotating it, it has angular momentum. So you can just think of a particle as being a tiny, let's say, a tiny spherical charged particle that is spinning about its axis. If you have a charged particle, charged sphere spinning about its axis, it will actually have a magnetic moment. So basically, a spin is a tiny magnetic moment. We don't really know if it's a small sphere spinning about its axis, but it behaves very similarly to that, except it's a quantum property. So it turns out that this angular momentum doesn't come in all, you can't spin faster and get more angular momentum. There's only one value for it. For an electron, spin half the value of the angular momentum, it's h power over 2. You just don't know which direction it is. And it turns out that when you do an experiment to measure that, you only get either that all of the angular momentum is up or down, depending on your measurement direction. You can do this measurement in any direction, but you always get two results. Either it's along your measurement direction, h bar over 2, or it's anti-parallel minus h bar over 2. That's it. Very peculiar. When you learn quantum mechanics, there are some books that start with kinetic energy and so on, and some books that just start with a spin and do all of the learn all of the principles of quantum mechanics with a spin. The advantage is that it's relatively simple. There are only two states. But the disadvantage is that really we don't have intuition about spin from our everyday life.
Okay, madam, thank you. There is another question in the inbox. So what is Meissner effect? Maybe you have already explained in your lecture. So you can
yeah, we can go back to that. The Meissner effect, let's find it. So the Meissner effect is basically the repulsion of magnetic fields from the interior of the superconductor. So if I have a superconducting state and you try to apply a magnetic field to it, then it will create supercurrents around its perimeter to push out the magnetic field. Or if you want, it creates an opposing magnetic field that exactly cancels the magnetic field inside. And this is why we can actually levitate a magnet above the superconductor. So here the superconductor at the bottom is cold enough to be a superconductor. It feels the magnetic field from the magnetic cube that we're trying to put on, and it pushes it out. And that's why we have that levitation.
Okay, madam. Thank you. This may be the last question. So do quantum mechanics meets general relativity at the Planck scale?
Oh, yeah, excellent question. So we have two, what we call modern theories, even though this already has been 100 years. One is relativity and one is quantum mechanics. And it seems that it's really hard to combine them. So we do have to think of relativistic effects. For example, spin-orbit coupling is a relativistic effect. Relativity is important when we have large velocities. So special relativity, we already know how to write theories with special relativity and quantum mechanics. All of the standard models is written The standard model for particle physics is written with special relativity in mind. So this is done. However, general relativity, which takes into account gravity, is very hard to put together with quantum mechanics. And our friends in particle physics, string theorists, loop quantum gravity, there are many ideas of how to go about doing that. I can't tell you that we have one solution of how to actually do that.
Okay, madam, thank you. So we have got another question. So if you allow, we can take that question.
Sure, sure.
Okay, so could you please explain superposition, nature of fundamental particle?
Yes, sure. So the easiest thing to think about in terms of superposition is basically in terms of spin. If you say that your particle doesn't necessarily have to have a single spin state, it in some superposition of spin up and spin down. So I can write my state as alpha times spin up plus beta times spin down. This is a state. It's a quantum state. It's well defined quantum mechanically, but it doesn't have a well-defined spin in the direction of my measurement. So now if I do a measurement, the system will give me the result up with probability alpha squared and the result down with probability beta squared. So therefore, we have to have alpha squared plus beta squared equals to 1. But this is a superposition. It's a state that I can't think of as classically, because classically you either have a well-defined property. I'm either here or there. I can't be in two places at the same time. Quantum mechanically, the particle can. It can be in a superposition. Unless we force the particle to decide by making a measurement, it will still be in a superposition. Just like waves, that their function is defined everywhere, in every place, at every time. And for a wave, classical wave, it doesn't collapse. I can't do a measurement of position of the wave. I accept it that the wave is everywhere. But for a particle, I want to be able to make a measurement, and at that point, it stops being a superposition. If you have a detector, you know, aha, the particle was detected here. But where was it before the measurement? I actually don't know. It was everywhere with some probability.
Okay, thank you, madam. So we can conclude our discussion session as we don't have any more questions. So thanks again, madam, for your excellent lecture and nice discussion session. It's a great honor actually to host you, madam. So the main aim of our program is to motivate our students, and I think by your excellent lecture, and I think some of our students may be motivated, and I think they will join this type of research very soon, and some of our students and colleagues have already did this type of works, and they might be later actually apply to your institute for higher study. So I think it will helpful for them. Thanks again, madam. And if you say something for those who are studying physics in bachelor level and master's level for the final time.
Yes. Okay. So thank you so much. It's really been a pleasure. I want to say to the beginner students, just follow your passion. I think we all do better when we find something that resonates with us. So follow your passion and don't let others tell you what you can and cannot do. You can do whatever you want if you do something that is making you happy, making you curious. So just keep at it, and you'll see that everything's possible. So thank you so much, and good luck with your future endeavors.
Thank you, madam. And we would like to say thanks on behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. And I will definitely invite you for a face-to-face session when the time will actually allow us. So thanks again. and see you very soon with another webinar. Bye.
Thank you.
Have a
Bye.
nice day.